This UCSD TV program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest programs.
Well, good evening, everybody. My name is Harry Helling. I'm the Executive Director here at the Birch Aquarium at Scripps. I'd like to welcome all of you this evening. Without further ado, I'd like to introduce the Director of Scripps Institution of Oceanography, Dr. Margaret Lehman.
Good evening, everyone, and welcome to the 7th Charles David Keeling Memorial Lecture. We have asked one of our own, Dr. Jeff Severinghaus, to speak. He is a global expert in climate change and paleoclimate and has been a leading force in putting together efforts to present present-day climate in historical context. This makes his appearance here very fortuitous tonight. So as you know, Charles David Keeling, the namesake of this lecture series, initiated what is now known as the Keeling curve, a measurement of CO2 in the atmosphere. It started right there off Scripps Pier, and it happened when then Scripps director Dr. Roger Revelle had just published a paper that had rocked the scientific community. Before his paper, everybody thought that all the CO2 that went into the atmosphere as a result of burning fossil fuels was going to be dissolving in the ocean. And his paper showed that that was not the case. But we didn't know how much was going into the atmosphere and how much was going into the ocean. And so Charles David Keeling came to Scripps and started working on measuring the CO2 in the atmosphere. At that time, the concentration in the that he measured in 1958 was 315 parts of CO2 per million parts of air. That was a concentration that you'll hear a little bit from Jeff about in terms of its historical perspective. But fast forward to this April, and the concentration is as high as 409 parts per million of CO2, a 30% increase over just since 1958. This year's burst has been fed a little bit by the El Nino, which has many impacts on climate, not just rainfall. Hand in hand with that news has been record-breaking warmth in the first 3 months of 2016, a heat wave in India that has been accompanied by 2 years of drier than average monsoon seasons, and of course we all are seeing what is happening not just this year, but over years in terms of the increasing number of wildfires like the one in Alberta. So they say that climate change response is about avoiding the unmanageable and managing the unavoidable. And this seems to be a year when both are going to be top of mind. So we need to know as much as we can, not only about what's happening now, but how that fits into a historical context and about the impacts of that. So I'm glad that Jeff is here tonight to talk with us about that. And in order to introduce him, Ralph Keeling, son of Charles David Keeling, is going to come up and tell us a little bit about Jeff and why he's such a great person to give this lecture.
Thank you, Margaret, and thanks to all of you for coming. So I want to say a little bit about how I got to know Jeff, because we go back to a point really before the present chapter of his career even started. He was one of these people who took a while to figure out where his passion lay. And I think he was oriented towards science mostly already early on, but he first tried out marine geology at UC Santa Barbara, and I think that went pretty well, except for some reason it wasn't something he wanted to stay with. And I don't know exactly every twist and turn, but there was a year or two doing Peace Corps type work in Nepal, and maybe some other twists and turns in there. But at some point he found himself at the Yale Forestry School, which is where I met him. I was giving a job talk at Yale, and I remember this very well because, you know, this is a kind of a scary thing to do. It was my first real academic interview kind of talk, and there were professors there, and I was under scrutiny. But the hardest taskmaster was this student sitting in the front row who just wouldn't give up. And then we got to talking afterwards, and we really kind of hit it off. He shortly after that went and did he was already looking at other options in geochemistry and did a PhD at Columbia, really at the Lamont Doherty Earth Observatory under a very distinguished geochemist named Wally Broker. And during his graduate years, he was still interested in some of the stuff I was doing. And so one of the things that will come up in his talk is a quest that has been part of his career, at least a theme of it since then, which is a quest for old air. So it's really about reversing the Keeling curve, going back in time. And among the harebrained ideas that he got foisted upon him was the idea that you could drill down into sand dunes, perhaps, and find old air. And that was something that he and I teamed up on. He came out here while he was at Lamont, and we went out to the Algodones Dunes, and he arranged for the rigger to go out there, one of the people from Long Beach who was probably mostly drilling for contaminants, but they got to drill one of the most pristine sites they'd ever done, drilled down, I don't know, 100 meters or something in a sand dune. And yeah, we found old air, or he found old air, but it was kind of contaminated old. It was stale. It was kind of like an old attic, so it wasn't quite what we were after. But as part of that, there was a marvelous photo taken of Jeff parading up the ridge line of a sand dune. It was such a beautiful photo that it got featured on the cover of the Scripps Explorations magazine, to some consternation, because there were people who were saying, what is a graduate student for Columbia doing on the cover of the Scripps Institution of Oceanography magazine? Well, we got him here eventually. So shortly after that, a postdoc, we got him back here. So he earned the right to have that picture on the cover. But his career has really blossomed since then. He's got lots of distinctions. Recently elected to the National Academy of Science, which is one of the highest honors in this country. A lot of his work is centered on a different way of getting old air, which is air from ice cores, which he'll tell you about. And he's also gone on sort of mining for old air at the edges of ice, and a lot of interesting discoveries about the past. It's really cutting edge insight into how the climate has done its twists and turns in the past, and it really sets a context for what we face now going into the future. So without further ado, Jeff?
Thank you, Ralph. Very kind of you. I have to say that this whole sand dune adventure was really cool, and it was really fun. I just like that kind of stuff that nobody's ever thought of before. And I have to credit Ralph for being willing to just team up with me on the basis of a phone call. I was interested in drilling into sand dunes for a completely different reason than he was, but we were both interested in drilling into sand dunes. He was looking for old air. I was looking for the tendency of heavy molecules to settle to the bottom under the influence of gravity. And so, so anyway, it was a very, very fun and creative, unusual project. And I think my graduate advisor at Columbia to this day doesn't understand it or why we did it. But it was great. So I'm going to talk today about ice cores and what I'm calling the reverse Keeling curve. Why do we call it reverse? Because we're looking backwards into the past to see what the atmosphere has done, as opposed to looking forward into the future, which is, of course, what Ralph and his father have been doing. So I like to start out this talk by thinking about the next generation here. That's why this is up here. And so why the next generation? Well, this climate change and ocean acidification issue is in many ways about future generations. It's a uniquely dangerous problem for this reason. It takes about 100 years, roughly speaking, to warm up the ocean in response to, say, greenhouse gas forcing by humans. And a lot of these greenhouse gases stay in the atmosphere for about 100 years. So that's kind of like a double whammy. That means that this is a seriously backloaded issue in the sense that we put gases into the atmosphere now, but the full effects aren't really going to be felt for 200 years. That means that we're making some serious commitments to future warming that maybe our great-great-grandchildren will experience. So in some ways, this is really all about the future generations. And they aren't at the negotiating table. So that's an ethical issue, I think, and many of us think that people whose lives are going to be affected are not present at the negotiating table. So I just want to keep that in mind as I go through all of this sort of fun and interesting stuff that I'm so lucky to get to do. So just a bit of background. The greenhouse effect, many of you have heard of this. The idea is very simple. The sun warms the surface of the earth because the atmosphere is transparent to solar radiation. The earth gives off radiation of its own, which is what we call infrared radiation, gives it off back to space. And that's how the earth cools off. And but some of that infrared radiation gets absorbed by gases like carbon dioxide in the atmosphere, making those gases a little bit warmer. And then those gases themselves radiate some infrared back down to the surface, as well as some back out to space. So think of the atmosphere as kind of like a blanket. It keeps the earth warmer than it would otherwise be. In fact, it would be 33 degrees centigrade colder if there were no greenhouse gases at all in the atmosphere. That's a pretty remarkable fact. Even though carbon dioxide is just a tiny fraction of the atmosphere, it's only about 400 parts per million now. That's 0.04%. That's a really tiny fraction. And yet, if there were no carbon dioxide and other greenhouse gases, the Earth would be 33 degrees colder than it is today. It would basically be an ice ball. The whole planet would be frozen over. It's hard to imagine that such a small amount of gas could make such a big difference. So I often give lectures to conservative audiences, frankly, and I always tell them that we love the greenhouse effect. The greenhouse effect is a good thing because without it, we would all be an ice ball. So thank goodness for CO2. Thank goodness for the greenhouse effect. We love CO2. So anyway, that's a good way to start out. But as my mother said, there is such a thing as too much of a good thing, right? And so we want, some CO2, but not too much. So actually, that's kind of the message, is that CO2 is a very powerful greenhouse gas. We like it, but we don't want too much of it. So how much does CO2 actually warm the Earth? Well, this gives you sort of a schematic feeling. It's a lot more complicated than this, but down on the bottom are some numbers, some concentrations. Before humans began burning fossil fuels, the concentration in the atmosphere was about 280. It's about 400 right now. And if we doubled it, it would be around 560, and that would give a warming of something like 5 or 6 degrees Fahrenheit, globally average. That just gives you a rough feeling. Now, society is well on its way if it continues its current trends of burning fossil fuels to get up to a tripling here. And you can see that would be 9 degrees Fahrenheit. So this would be a radically changed planet. It would look something like this, where the red colors here represent about 9 degrees Fahrenheit. And so you see that, we're looking, this would be a very, very different planet. The oceans don't warm as much. That's because of the fact that water is very good at soaking up heat, and it takes 1,000 years or so to really warm up the ocean. So the land warms first and fastest. But anyway, I don't think I need to tell this audience that this would be a very, very different kind of planet with some possibly very severe drought and probably failed states, social chaos, war, all kinds of nasty things like that. How do we know that humans are causing this? This is a question I often get. Well, basic physics tells us that CO2 traps heat. This is not new science. This was discovered in 1861 by the British physicist John Tyndall and been studied in great detail by our very own Department of Defense. Why? Because they were trying to figure out why heat-seeking missiles sometimes got confused by the CO2 coming out of the engine of enemy aircraft. Well, they did a lot of very careful study on showing how CO2 soaks up heat, and they managed to figure out how to teach the heat-seeking missiles to avoid those particular wavelengths of infrared radiation that get soaked up by CO2. So anyway, long story short, we know an enormous amount about the basic physics, and it says unequivocally that CO2 traps heat. So that's just simply not up for debate. But even if you don't like physics, you can still go to astronomy and look at our neighbor planet, Venus. Venus has about 300,000 times more carbon dioxide in its atmosphere than we do. And it's got a surface temperature of 864 degrees Fahrenheit, which is warm enough to melt lead. So that's the greenhouse effect in action right there. If you don't believe physics. The other way we know that humans are causing this is that we have this very, very detailed and precise and unchallenged record, the Keeling curve of atmospheric CO2, combined with the known records of burning fossil fuel. Why do we have those records? Because fossil fuel is a valuable commodity, so people tend to keep accurate records of how much was burned and how much was sold. So the combination of these two show very clearly that the amount of excess CO2 in the atmosphere is due to human burning of fossil fuels. And here is the Keeling curve, since we've been talking about it. I just downloaded this from the website that Ralph maintains this afternoon, and you can see that the record starts at about 315 parts per million, and that's a number that Margaret mentioned in her introduction. That's the value that Charles David Keeling kept getting when he would go to places with clean, remote, uncontaminated air, like up in the Sierra Nevada, or very far away from land out in the ocean. And indeed, he set up the monitoring station on the summit of Mauna Loa in Hawaii to get away from contamination. And so he was basically the one that figured out that there really is such a thing as a stable background concentration of CO2 in the atmosphere. Most scientists at the time believed that CO2 would be wildly variable everywhere, and you wouldn't be able to ever get a definite reading of the planet's CO2 concentration. But he knew better because he really listened to the meteorologists, the weather people. And anyway, so this curve already, in a few years after he started measuring, told us that something was changing, something was going on. It was creeping upwards, and already that was understood to be due to fossil fuel burning, so it didn't take long. So here we are at the present. This is the concentration 2 days ago. So we peaked at about 409. Now it's coming back down again. So that's the Keeling curve, and it's hard to overstate the impact of this record. I just want to mention the other Keeling curve while we're at it, though. The other Keeling curve, also known as the Ralph Keeling curve, gives you something like this. Here I've plotted the CO2 concentration on the bottom axis. And so what you see there is that this is from about 1989 up to the present, or I guess this is 2000. So CO2 has been increasing along this way. And at the same time that CO2 has been increasing, oxygen, which Ralph is measuring, has been falling. And it's been falling by quite a bit. And the dots show the trend on this kind of a plot of oxygen changing with CO2. And so what's interesting about this is that this line here is the line you'd expect for burning fossil fuel, because fossil fuel consumes one oxygen molecule for pretty much every every something like one carbon atom that's burned to fossil fuel. I think the ratio is actually like 1.4 to 1 or something. Anyway, what this tells us is that the amount of oxygen in the atmosphere is not decreasing quite as fast as it ought to be decreasing due to fossil fuel burning. Very interesting. And, this is a really important discovery. Ralph was able to show that the biosphere on Earth is actually growing slightly. And the reason you can tell that is that when plants grow, they make oxygen, right? So they replace some of the oxygen that's being consumed by fossil fuel burning. Just going on now to this human causation question, how do we know this? One of the most easy to understand and sort of dramatic ways that we know that humans are causing this has to do with something called isotopes. Now, isotope is just a different flavor of an element. So carbon, for example, has two flavors. It has carbon-12, which is the abundant isotope, and it has carbon-13, which is kind of a rare isotope. About 1 out of every 90 is a carbon-13. And so the isotopes that have been measured in the atmosphere over time, along with the concentrations, can show us that the fossil fuels are the cause of the current rise in CO2. But to do that, we have to go back into the ice core record. So here's what an ice core looks like. Polar ice cores are unique in that they contain little bubbles of air, and they also have annual layers, which is really convenient because then we can just count annual layers like you do with tree rings to get the age. So we know the age, we know we can measure the gases in the ice core, so we can know what the atmosphere was like in the past. Hence this idea of a reverse Keeling curve going back into the past. This is what the air bubbles actually look like. And this is just a little slice, a thin slice of an ice core. And there's lots of air. As you can see, about 10% of the volume of glacial ice is actually made of air, which is really a lot, actually, for geochemists. It's pretty cool. We get to work with abundant samples of past atmosphere because ice has so much air in it. And this is what the CO2 concentrations from the ice core look like plotted on top of the Keeling curve. This is actually the South Pole Keeling curve. It's often not mentioned that at the same time Charles David Keeling began measuring at Mauna Loa in Hawaii, he also began measuring at the South Pole. He had enough intuition to realize that those two records could be very different from each other because of the fact that it takes about 1 year for the atmosphere to mix between the two hemispheres. And there's enough outgassing of CO2 from the ocean that they could be different. In fact, he discovered they were different. So anyway, this is the South Pole Keeling curve, and these are Antarctic ice cores, which should have the same values, and they do pretty much. The ice core values are a little more scattered, but within a few parts per million, they do agree. So this confirms the integrity of the ice core record, confirms that there's not any kind of bias due to, say, gases diffusing out of ice cores. And so here's the longer record from ice cores. This is the last 1,000 years. Here's 1000 AD coming up to the present. And this part of the curve is the Keeling curve. And then all of this is the ice core records, ice core values. And what you see is that the recent rise is quite unprecedented. For most of the last 1,000 years, the concentrations of CO2 were rather steady, around 280 parts per million. So that's right away a suggestion that humans have done something, because if this was nature doing it, you might expect this whole thing to be rising. And if we go to a longer time scale, we see something similar, that it's been stable for a long, long time at about 280 parts per million. That seems to be the natural level. So what about carbon-13 now? Now I'm just going to show you the carbon-13 data that are superimposed on top of this regular graph. So these are also from an ice core, the same ice core. And so here's the concentration. Here's the isotopic ratio of carbon-13 to carbon-12 in those same air bubbles. And what you see is that there was a long period of very steady concentrations of carbon-13. Don't worry about what these units mean for the moment. Just a relative deviation. And then all of a sudden, carbon isotopes took a nosedive right around the time that the concentration shot up. And this time here is about 1850. Well, that's about the time that widespread coal burning began, the beginning of the Industrial Revolution. So it turns out that carbon-13 is an excellent tracer of fossil fuel CO2, because it's fossil fuel CO2 is very depleted in carbon-13, and so as fossil fuel CO2 is added to the atmosphere, it by dilution it draws down the atmospheric C13 abundance, and it does so in a way that's extremely complementary to the concentration. So this is about as close as you can get to a smoking gun. And I use this term smoking gun because over the years so many people have asked me, can't you just show us the smoking gun? And, and so okay, here it is, the smoking gun, you know. So the whole 10,000 years is now shown in this image, again from the Keeling curve website. And again, it's not changing hardly at all. It's very, very stable over the last 10,000 years. And then boom, here's this sudden uptick due to the Industrial Revolution. And here we are today, above 400 parts per million. So you can see that this, whatever it is something that's very, very extraordinary in the context of the last 10,000 years. All right, so now we're going to go back even farther in time along this reverse Keeling curve. Instead of just 10,000 years, I'm going to show you the full 800,000 year CO2 record. So this is the CO2. Here we are today around 400, and you can see that it was at about 280 for most of the last 10,000 years. Now we're going very, very much farther in time. This is back 800,000 years. By the way, that is as far as the current ice core record goes. We haven't yet found any ice that's older than 800,000 years, but we're looking. I'm part of a group that is trying to extend it back to 1.5 million years. Why 1.5 million? Well, it turns out that the ice ages changed about 1 million years ago, and so we think that we don't understand why they changed. They changed from a period of about 41,000 years, which is a well-known period for the Earth. That's the period of the tilt of the Earth's axis increasing and decreasing every 41,000 years. So when the tilt of the Earth's axis increases, the seasons get stronger. The reason we have summer and winter, of course, is because the Earth's axis is tilted. And so the seasons get stronger, and that tends to melt off the ice at the poles. And so you basically destroy ice when the tilt is large, and you build ice when the tilt is small. And so that's a well understood process. And so, but about 1 million years ago, the cycle changed to a very enigmatic and irregular 100,000-year cycle, which is what you're seeing here. And when we say 100,000-year cycle, we're kind of taking some liberties. It's not really 100,000. Sometimes it's 80,000. Sometimes it's 120,000. And it's just really irregular. It's got a lot of abrupt changes in it. So really, we don't understand what happened about 1 million years ago. And this is kind of an interesting time, too, because we humans got our start about 2.8 million years ago, probably because the ice ages started. We were all living in trees and eating fruit about 2.9 million years ago, and about 2.8 million years ago, the climate got cool and dry. So we all came out of the trees, and we started doing things like hunting animals and eating lion kill and collecting roots, things that you would have to do in a drier, more sort of grassy savanna type climate. So these things are connected with the whole story of how humans came to be as well. Anyway, I digress. But this record is not actually all that relevant to the whole story of human causation, but it's kind of interesting in its own right. I think it tells us a lot about the way that the natural climate system can change rather dramatically over time. The temperature in Antarctica is shown here in this curve, and you might notice that there's a lot of similarity. If you just by eye, I think you can tell that these curves actually look a lot like each other. Now, I won't show you this, but if we zoom in on these periods when the temperature seems to be shooting up and the carbon dioxide seems to be shooting up, we see a very interesting fact, which is that the temperature changes first and the carbon dioxide changes second. So obviously, the temperature change, at least the very first part of it, is not being caused by the carbon dioxide change. So this is not really primarily a greenhouse effect. There is some greenhouse effect in there, but it's in a way it's not surprising, because we know that these irregular 100,000-year cycles have something to do with the Earth's orbit. Why do we know that? Because every 100,000 years, the Earth's orbit becomes round. And when the Earth's orbit is round, there's not really any one particular time of year when the Earth comes close to the sun. And we know that when the Earth comes close to the sun in June, the glaciers all melt. Why is that? Well, because there's a lot of land in the northern hemisphere, and so June is melting season on Earth, basically. The southern hemisphere doesn't have a lot of land, so it can't have a lot of big ice sheets. So we know that because the Earth's orbit is basically causing these big ice ages to come and go, that the temperature should change first, and then the carbon dioxide should change, presumably because the carbon dioxide is coming from the ocean and coming into the atmosphere. We know that when you warm up the ocean outgasses carbon dioxide into the atmosphere. So this is not the smoking gun of human causation. In fact, this tells us something very different, which is that the Earth has something called a feedback. And you may have heard that word before. A feedback means that a process ends up causing more of itself to happen. It feeds back onto itself. In this case, the sun is warming the Earth and melting glaciers, which then causes the ocean to burp out a little extra CO2, which in turn warms it even more by the greenhouse effect. And actually, it's not a terribly powerful effect. This relatively small change in CO2 adds about 30% to the total warming here. So it's less than half of the total warming. So this is not very much compared to what humans are doing and what humans are going to do. This is about 80 parts per million change, and humans have already raised it something like 120 parts per million, and we're well on our way to go to 200. So I just want to describe in a little bit more detail this issue of how the temperature in Antarctica changes first, and then the CO2 rises, and then finally the global temperature rises even later than that. There's a myth The ice core record shows that carbon dioxide rose after temperature began warming at the ends of ice ages, which that part is true. The part in black is true. The false part is the red part. Therefore, carbon dioxide does not cause warming. So this is a myth that has been repeated many times on Fox News. The fact is that ice ages are ended by changes in the Earth's orbit, so it's not surprising that temperature starts changing prior to the onset of CO2 rise. CO2 then acts as an amplifier or a feedback, which increases the total amount of warming by about 30%. So, in contrast, humans are directly adding CO2 to the atmosphere now. In that sense, ice ages are not a good analog for the current situation. So, in some sense, this whole issue of which came first in the ice age context is a red herring. It's just not very relevant to the current situation. And when we look at these ice age cycles of CO2, they are small compared to what we're doing. This is business as usual, you know, and it could go even higher, but this is just a sort of a standard business as usual for the end of the century. We are radically changing the CO2 concentration much, much more than Mother Nature did. So just to drive that point home, let's think of an analogy. We know that CO2 and temperature are changing essentially together, with temperature leading just a little bit, a few centuries before. And so one way to think of this is that if you overspend your credit card, you go into debt. And then you have to make interest payments on the debt, which gives you more debt. So, which came first, the debt or the overspending? Well, yeah. So, obviously, the interest payments come after you went into debt. So, interest lags debt. How do we know that interest adds to debt? Well, we can't explain the size of the debt without interest, and also the economics profession tells us that it does. So, then if we go to the climate now, the Earth's orbit causes warming, which then causes some CO2 rise, which then causes more warming. And how do we know that the CO2 rise is causing more warming? Well, physics tells us so, the profession of physics. And and we can't explain the size of the warming without including the greenhouse effect. In other words, we only get about 2/3 of the warming that we actually observe if we don't include the effect of the carbon dioxide. I want to say something about some other greenhouse gases that are important, even though in some ways CO2 is the one that is by far and away most troubling, because it's very large in its total impact on warming, and it also causes ocean acidification, which the other greenhouse gases don't. Ocean acidification happens simply because CO2, when it mixes with water, becomes an acid, carbonic acid. And so it tends to dissolve the shells that the sea creatures make. So really there are sort of two CO2 problems: global warming on the one hand and ocean acidification on the other hand. So that's why I tend to focus on CO2. But some of my colleagues focus a lot on methane, and that's okay. Methane is also going up rapidly. Here's the methane record from the northern hemisphere and here from the southern hemisphere. They've been going up. Humans have basically almost tripled the concentration of methane over the Industrial Revolution, mostly through agriculture, cows, but also landfills and rice agriculture and lots of different things. And here's the Ralph Keeling curve, the oxygen going down at the same time. And then another important greenhouse gas is what we call nitrous oxide, also known as laughing gas. And laughing gas is actually no laughing matter when it's on a planetary scale, because it's a very powerful greenhouse gas, and it has a lifetime in the atmosphere of 140 years. So when we put N2O in the atmosphere, we're making a very serious commitment to future warming, whereas methane only stays in the atmosphere for 8 years. And so in some sense, if you want to put put methane in the atmosphere, well, you're going to suffer in the, over the next 8 years, some extra warming. But if you put N2O in the atmosphere, or CO2 for that matter, into the atmosphere, you're basically making a commitment for future generations to suffer some warming. So there's a qualitative difference between methane and the other two greenhouse gases, and especially in terms of the whole ethical problem of future generations not really being part of the negotiation. So here's the N2O record going up, and these are now in parts per billion, 300 parts per billion instead of parts per million. But because it's such a powerful greenhouse gas, it does have a significant impact. So these are all direct atmospheric records, but they weren't started until sort of the mid-70s. And so to get information about these gases before that time, we have to go to the reverse Keeling curve again, to the ice cores. And that's what these look like. Here's the ice core record over the past 2,000 years for methane in blue and nitrous oxide in black. And nitrous oxide is plotted on this axis over here, and methane is on this one. So methane has almost tripled, as I said, sort of gone from something like 800 up to 1800. And these were pretty flat. As you can see, they weren't changing a whole lot during the last 2,000 years. And then this is going back deeper into time. This is a recent and unpublished ice core record from the West Antarctic ice sheet divide. And this is work of Sean Market at Oregon State University and Ed Brook at Oregon State University. And what you're seeing here is the methane concentration in red, although it doesn't have an axis. But what's clear from this is that methane has a lot of rapid ups and downs, and this is due to what we call abrupt climate change. So I'll say a few things about abrupt climate change. CO2 has more gradual variations, but you can see that there's some interesting little things going on here. This is the end of the last ice age, when CO2 was rising rapidly from about 190 parts per million to 280. And so this has given us a wealth of information and new puzzles, things to think about, how these gases respond to climate, because of course there's no human actions in here, and most of this is a response to climate in one way or another. And this is a more complete picture of all these ups and downs, which we call abrupt climate change. On the top is the Greenland temperature, and you see that there's these little steps that look like they happen really fast. Well, they did happen. It turns out they happened in only about 30 years, or even less, maybe half of this change in 1 year. And this is a proxy for temperature. So these are basically abrupt warmings with more gradual coolings following them. The green record is the one you just saw in methane. It looks like Greenland temperature and methane both go very closely together, and that we've learned over the years that the reason is that when the northern hemisphere warms, the tropical rain belts all shift northward, and it rains more on land, which it makes more methane from tropical swamps. Basically, methane is made in swamps. And from Antarctica, this is the Antarctic temperature, we see a very interesting pattern. The Antarctic temperature always seems to be warming while Greenland is cold, and then when Greenland warms abruptly, Antarctica goes into a long cooling phase. And this is what's become known as the bipolar seesaw, because it seems like when the north is warm, the south is cold, and vice versa. And so this has, over time, been understood to be the result of the North Atlantic Ocean circulation switching off and on. When it switches on, you get an abrupt warming of the northern hemisphere, because the ocean circulation brings all this warm water up north into the area of northern Europe, where the water sinks to the bottom of the ocean and then flows southward as this blue current. It's very cold deep water, as we say. So that makes a kind of an overturning or a conveyor belt circulation. And one of the worries of the past, say, 2 decades has been that this so-called overturning circulation might shut down suddenly. Some of you may remember a movie called The Day After Tomorrow. I don't know if any of you saw The Day After Tomorrow. Well, anyway, that was a sort of a fictionalized version of this concern that this might shut down. Anyway, the good news is that in the past 20 years or so, we think we've learned that this is unlikely. So it's one less thing to worry about. You can check that off your worry list. The circulation is probably not going to shut down. How do we know that? This is from the recent IPCC report. And I want to draw your attention to this figure in particular. This is the Atlantic here and the Pacific. And you can see that right now, in the last few decades, the Atlantic has been getting saltier, dramatically so, actually. This is a big change for physical oceanographers. And the Pacific's getting fresher. So why is that? Well, it turns out that as the globe warms, humans are warming the globe is warming, there's more water vapor in the atmosphere. Why? Because warm air holds more water vapor than cold air. So there's more water vapor in the atmosphere, and the way the continents are configured, all that moist air blows out across Panama into the Pacific. So the Atlantic actually loses fresh water through the atmosphere across Panama, but it doesn't really get any vapor, because of Africa's in the way. And so basically, in a warm world, we now believe that the whole Atlantic gets saltier. And what does that do? Well, salty water is dense, and so it sinks to the bottom more easily. And so it actually encourages that sinking around Greenland that we saw before. So this salt actually tends to stabilize the overturning circulation. So in a warm world, we're probably going to have a stronger overturning circulation rather than a weaker one. So that's, in some sense, good news. My take-home message is that human-caused climate change is a fact. It's supported by an overwhelming amount of evidence. And when I say overwhelming, I mean really overwhelming. It is about as clear as the evidence that cigarette smoking causes cancer. It really is that clear. Huge amount of evidence, very, very persuasive. That's why something like 97% of climate scientists agree with this view. The 3% who don't often have very convoluted explanations for why they don't, and many of them work for the fossil fuel industry. So yeah, you can take this one to the bank. It is a fact. It's not in dispute. Another point which I didn't have time to mention, but you could see from the records of past climate that there are very significant natural variations in climate on this planet that we inhabit. So we should expect those to continue. We should expect natural variations in the future, and they're going to be superimposed on the human-caused warming trend. So if we have snowstorms, epic snowstorms in Boston, that isn't proof that global warming is not happening. It just means that there's natural change that's going on, superimposed on the human-caused warming. The other thing to realize about this is that some of these natural variations take 10 to 30 years to play out. And so, for example, there was a period between 1945 and 1975 when global temperatures were essentially flat or even went down a little bit. And that was probably one of these natural variations. And so essentially that's not unexpected. Based on what we see in the past, we know that the natural system has lots and lots of variation, so we should expect to see that again. But on average, the trend will be up. Another important point, which I didn't have time to talk about, is that global warming tends to cause drought locally, even though as the world warms, the total amount of rainfall on Earth increases, just because warmer air holds more water vapor. So drought is in our future, sad to say, and drought is probably a bigger impact on ecosystems and societies than temperature per se. Temperature, well, 2 or 3 degrees, that's something we deal with every day, right? But drought is a bigger deal, especially for those of us in sunny, dry Southern California. But maybe more importantly, fragile societies in places like sub-Saharan Africa are at risk in the next 100 years for basically being failed states because people suddenly have nothing to eat. And what do people do when they have nothing to lose? Well, they usually go to war. They do things like engaging in genocide. In fact, the Rwandan genocide was probably partly caused by a drought. And the Syrian conflict is also caused by a drought. And so many scientists say that the Syrian drought is actually partly caused by anthropogenic global warming. So that's kind of a taste of what we have in our future. It's not so much the temperature, it's the social chaos. And then finally, we can expect about 3 feet of sea level rise in the next 100 years. And so that's something to factor into planning. If we rebuild, an airport somewhere, we should think about that. That's a very, very strong prediction. It's almost certainly going to happen. So what's the solution to all this gloom and doom that I've told you about? Well, the solution is actually very clear. It's actually pretty simple. We have to just totally decarbonize the global economy. With the industrialized and wealthy nations taking the lead, that means us, because we actually have the means to do it. Other countries just aren't wealthy enough to do it, but we can do it. And we can do it without a whole lot of pain either. That's the good news. We don't have to freeze in the dark. We can use the abundant wind and solar energy that we're blessed with. And we can also create great jobs in doing it. We can bring a lot of those jobs back from China by becoming the world's manufacturer and exporter of green technologies. And we can do that right here in San Diego. So we can have basically a stable climate and a great economy all at the same time. So thank you very much.